Sorry, I did not open up the mic. So we ended at slide 39. And we'll see that for a specific system, you can actually change the uh, operating pressure, and then the corresponding flow rate and the total pressure will also change. So when you try to modulate the fan duct system, there are some different methods. For example, you can use dampers. You can use terminals with inlet vanes, and you can use the you can use the change of the fan speed. Okay, so we'll first look at the modulation of fan duct system using dampers. Okay, when you are actually apply dampers to the fan duct system, you are actually changing the system curve. For example, here S1 is corresponding to the damper at the first location, and then when you further try to close up the damper, the duct system resistance will increase, and you will get a new system curve here. And then for the third part, you will get a this is when you are trying to further close up the damper, and the system curve, the system resistance is further increased. So by changing the damper position, you change the system curves, and the system curve is changed like this, S1, S2, and S3, and the corresponding operating pressure will also change. So point A is the operating pressure corresponding to system curve S1. Point B is the operating pressure, point corresponding to system curve S2, and C is corresponding to SC. So we'll see that from point A to point C, the flow rate will decrease, and the pressure difference will increase. And so this is how it looks like on the modulation range is point A to point C. Okay. So volume control damper is a prevalently used damper in HVAC system. So you can see that in terms of damper position, it can vary from fully closed to fully open. So if we assign fully closed to 0 and fully open to be 100%, and we can form our horizontal axis. And the vertical axis of this chart is the resistance of the system. So you can see that from fully closed to fully open, the resistance will first of all decrease rapidly, and then it will gradually decrease. So that means from fully closed to like 50% open, the resistance will change a lot. And then if the damper is already half open, and when you further try to open up the damper, the resistance actually will not change that much. So this is the volume control damper. So for this kind of modulation process and method, it cannot actually modulate the operating point that precisely, because the damper resistance is really difficult to control and to locate. Okay, so the second method is to use this VAV terminals with inlet vanes control. So the modulation curve is here, and the system operating point actually here changes with A, B, C, D until point H here. So for inlet vane opening, for different inlet vane opening, our fan characteristics curve will change. The inlet vane is the corresponding to the fan inlet vane, and the system curve, the fan performance curve, the system curve will change from S1 until S8 at its corresponding inlet vane opening. Okay, so the inlet vane will affect both the fan performance curve and the system curve. So as you can see here, we start with the inlet vane opening at 90 degrees, and then our fan performance curve is FT1, and the system curve is S1. So this is our operating point is point A. And when we change the inlet vane opening to 80%, our fan performance curve will be changed to FT2, and the system curve will be changed to S2. So our operating point will be changed to point B. So similarly, we can form point A until point M, and this will form the modulation curve. And on the modulation curve, the modulation curve is actually corresponding to how, for this specific system, how our operating point, how our pressure increase or pressure difference changes with our flow rate. And on our modulation curve, every point on our modulation curve is a system operating point corresponding to different scenarios. Okay, so these two figures, the first figure is the modulation curve with VAV terminals, and the modulation range can be changed from point A until, as you can see here, point H or point M here. So from A to B to C is the modulation curve with VAV terminals. So if it's without VAV terminals, then the inlet vane control will only change the inlet vane control will only change the fan characteristics. So we have the first, the second, and the third here corresponding to A to B to C. And this figure is similar to the figure here. Oh, okay, so it's not. Oh, sorry. So as you can see here, point A to small point B and small point C. As you can see here, our small point B and small point C is actually on the same system curve. So if the system is without VAV terminals, and when you change the inlet vane, it will only change the fan characteristics, as you can see here, the first, second, and third fan characteristics. So the change happens in also the change happens also in the first figure. And the second figure is just the corresponding curve here. Okay. So you can also modulate the fan duct system by varying the speed fan. So when you vary the speed fan, you are actually changing the fan characteristics curve, as you can see here. The first curve is on corresponding to N1, and the second curve is corresponding to N2, and third curve is corresponding to N3. So if the system is with VAV terminals, then the system curve can also change S1, S2, and S3. So S1, combining S1 and N1, we can obtain point A, and combining S2 and N2, we can obtain point B, and combining S3 with N3, we can obtain point B. And the modulation range also is here, and we can find the corresponding modulation curve here. So and also by comparing the speed control with the inlet guide vane control of the fan, using variables, speed control is generally more power saving compared to this inlet guide vane control. Okay, so this is for lecture number 9, fan duct system. So we will be covering the tutorial question in the tutorial session later. Okay, so now we are going to move on to our last lecture, and this lecture will not be tested, so we will only briefly go through lecture number 10, control of ventilation noise. And so first of all, we will be looking at the background. This is a typical air conditioning system for the air side, obviously, and the major noise source is the fan. And it can be transmitted through duct and flanking. So if the system is poorly designed in terms of the noise control, you will hear noise, and it will actually sometimes disturb our production inside this conditioned environment. Okay, so this is first we will be looking at the noise transmission paths in a ventilation system as shown here. So obviously the major source of the noise is the fan, and the first source of the noise transmission is the airborne noise from the plant room, and the plant room is where the fan is normally located. In the plant room we have air handling units. Okay, so it's marked as here, point part 1. And secondly, we have structure-borne noise as shown here. So starting from the source of the noise, the fan, the vibration can be conducted through the structures, as you can see here, the fan, the duct systems, and the terminals. Oh, sorry, not duct system. It's the noise can be, the vibration can be transmitted through the structure. So the plant room is located in this example is located on the rooftop, and it will the vibration can be conducted through the structure as it's connected to the fan. Okay, so as we can see here, so the noise can come from the ceiling part, the walls, obviously. So those structure-borne noise. Okay, so the third type is the duct-borne noise. The vibration will also be transmitted through the duct, as you can see here. So it can be transmitted through the duct, obviously, and it can be transmitted to the terminals, as shown here, as demonstrated here. Okay, so the fourth noise transmission path is the breakout of duct-borne noise, as point 4. So if there are some breaking points along the duct, it will also transmit noise, as shown here. Okay, so this slide shows the acoustic energy flow here. So we have the fan noise, primary fan, and the fan noise energy can be transmitted to the duct system, and the duct system is the main transmission path. Okay, and the fan is the primary source, and the secondary sources are bands, dampers, and etc. When our flow goes through the bands and dampers, and it will obviously hit on the damper and hit on the bands, and that will create also lead to vibration and further lead to noise. So this is the bands and dampers and etc. are secondary sources. So both the primary source and secondary source will input energy to the main transmission path, which is the duct system. Okay, and so through the duct system, part of the acoustic energy will be transmitted through the duct walls by flanking energy, shown here. And the noise energy will be directly transmitted to the receiver or occupants of the ventilated spaces. The primary fan will transmit the acoustic energy to main transmission to the duct system. It will also take the secondary transmission path to building structure, duct supports, and etc. through fan casing, radiation, mechanical vibration, or flanking energy, as shown here. Okay, and all the secondary transmission paths through building structure and duct supports will be transported to occupants of the non-ventilated spaces and also occupants of the ventilated spaces. By looking at the figure here, so the building structure and duct support, such as building structure as shown here and duct supports as shown here. In this figure, the top part of the space is a non-ventilated space, and the bottom part of the space is ventilated space, as it directly shows supply grills here, 1, 2, 3. However, the duct will go through the upper space and also the upper space have building structures. So through the energy flanking, the vibration or the acoustic energy flow, some part of it will be transmitted also to the upper space. Okay, so this is the acoustic energy flow in a ventilation system. Okay, so the concept of the noise fundamentals includes intensity, power, sound pressure level, and the sound power level. So the most important part to our application is the sound pressure level and the sound power level. So both of them will first of all take a reference here. So for sound pressure level, the reference pressure is 2 times 10 to the negative 5 Newton per square meter. And the sound pressure level is equal to 10 times log 10 to the sound pressure, the actual sound pressure. So this is the actual sound pressure divided by the reference pressure time, and you take the square. And similarly, the sound power level also have a reference power, and the reference power is 10 to the negative 12, and the unit is watt. And the sound power level can be calculated by 10 to the log 10, and the actual sound power divided by reference power. So when the sound pressure is doubled, the change of sound pressure level will be doubled. Okay, so as you can see here, when the sound pressure is doubled, we will first look at how the change of sound pressure level looks like. So the sound pressure level 2 equals, when you apply this equation, equals 10 to the log 10, and on the top part it will be 2 times pressure square divided by the reference pressure square, and then it will be equal to 10 times log 10 pressure square divided by reference pressure square plus 10 times log 10 to the 4. Okay, so the first term is actually the sound pressure level corresponding to this specific pressure, and the second term is calculated to be 6. So that means when you SPL1 plus 6 equals SPL2, and the sound pressure corresponding to SPL2 is 2 times the sound pressure corresponding to SPL1. So if the sound pressure is doubled, the change of sound pressure level is 6. And what we can do is we can use the similar calculation to sound power. So our original sound power is W here, and this is corresponding to sound power level 1. So sound power level 2, by substituting to this equation here, equals 10 to the log 10, 2 times the sound power divided by the sound power reference. And then it's equal to 10 times log 10 is original sound power divided by the, this should be W reference, divided by the sound power reference plus 10 to the log 10 to the unit of 2. Okay, so the first term is actually the expression of sound power level corresponding to W here. And the second term is calculated to be 3. So if the sound power is doubled, the change of sound power level will be 3. Okay. So I have listed a example here, and you can calculate the sound pressure level by yourself. And I'm going to leave the example here for you to solve after class. Okay. So when you actually, you can also apart from the previous calculation method, you can also refer to this table when you're trying to add up 2 sound levels. Okay, so if the difference between 2 sound levels, for example, is 3, and when these 2 sound sources added up together, then the final sound level will be higher level of the 2 plus 2. For example, if we have 2 sound levels, and the first sound level is 7, and the second source, for the second source, the sound level is 10, and then the 2 sources are put inside one space, and you are asked to calculate the final sound level. And what you do is you go to this table and you found that the difference between the 2 levels, which is 7 and 10 respectively, and the difference is 3. And then you refer to the value at right hand side, and you immediately will know that if you have 2 sound sources, one is 7 dB and the other is 10 dB, and you add them together, and the final value will be 10 plus 2. It will be 12. Okay, so this is the table you can refer to. Okay, so this figure also, this slide also shows the calculation of noise levels. So you can consider unidirectional spherical propagation and unidirectional hemispherical propagation, propagation of line sources, and prediction of a sound pressure level at some distance from the source. Okay, so the noise generation mechanism from the fans basically is the we have turbulence wake here, so it will cause a vibration. And actually, it can be divided to several conditions. The first figure shows the impeller blade in a smooth flow, so we only have some turbulence wake here. And if the impeller blade is in a disturbed flow, actually the scenarios are different when the blade is passing through the turbulent flow, or the blade is cutting through wake of a fixed optical. And both of them, all of them will generate vibration, and that will cause the that will cause noise. Okay. The fan operation will also have some effect on noise it will cause vortex noise. So the vortex noise level will first of all decrease, and then it will increase again with the it will decrease and then it will increase again with the change of the volume flow. Okay, so the sound power level can from different fans. For example, in a HVAC system, there might be different fans, and this figure here actually compares the sound pressure level from different types of fans, including axial fan, forward curved fan, backward curved fan, and two-stage axial fan. So if you would like to know which fan can cause the most sound power level in designing your system, you would like to maintain a relatively low sound level, you can refer to this figure here. Okay, so I'm going to end here. The remaining slides are for your own study, and you can apart from the slide here, you can also refer to our study guide. Let me see. Not here. Air conditioning and ventilation. You can refer to control of noise in ventilation system, chapter number 8 on the study guide for more study materials regarding the ventilation noise. Okay, so I'm going to end here today, and see you later in the tutorial room where we will go through the tutorial questions in tutorial number